Have you ever gazed at the night sky and felt small? Now, imagine shrinking inward, past mountains, grains of sand, even your own cells, until a single atom looms like a universe. As you shrink, the world transforms. A blade of grass becomes a skyscraper, a speck of dust a mountain range. Soon the air itself dissolves into a blizzard of particles. Nitrogen, oxygen, each in constant, frantic motion. You've entered the atomic realm, where solid objects are mostly empty space, and reality is a shimmering lattice of points of light. Here, particles can be in many places at once, and the certainties of our world dissolve into probabilities. Yet, from this chaos, everything emerges: rocks, sunlight, life itself, all born from the dance of atoms. Our destination, a single carbon atom, its dense nucleus orbited by a ghostly cloud of electrons, separated by vast emptiness. This is the fundamental architecture of our universe. What is an atom? The ancient Greeks called it atomos, indivisible. They imagined atoms as the smallest building blocks of matter. Every substance, water, iron, silicon, even the stars, is made from these tiny units combining in endless ways to create the world's complexity. There are just over 100 types of atoms, the elements listed on the periodic table: hydrogen, oxygen, carbon, gold. Each element is defined by the number of particles inside it, and by combining them, we create everything imaginable. But atoms aren't indivisible. They have structure, a nucleus at the center, surrounded by electrons. Electrons, fundamental particles with negative charge, give atoms their ability to bond and form molecules. The discovery of atomic structure revolutionized science, revealing a universe far stranger than we imagined. The solid ball of the Greeks was replaced by a dynamic system of particles and forces. Understanding this structure is key to understanding matter, energy, and the forces that shape the cosmos. The atom is not the end of the story. It's the gateway to the universe within. Let's dive into the heart of our carbon atom toward its dense nucleus. The journey from the electron cloud to the core is a vast voyage across emptiness, one of the most counterintuitive facts about reality. When you clap your hands, you're not truly touching, you're feeling the force of electrons repelling each other across atomic voids. The nucleus, though tiny, contains over 99.9% of the atom's mass, packed into a space unimaginably small. If an atom were a cathedral, its nucleus would be a fly at the center, yet a teaspoon of pure nuclei would weigh billions of tons. Here we find protons and neutrons. Protons define the element. Each carrying a positive charge. Neutrons, neutral, act as nuclear glue. The number of protons determines the element. Change it, and you change the atom's identity. Neutrons stabilize the nucleus, spacing out protons and overcoming their mutual repulsion. Without neutrons, only hydrogen could exist. The diversity of elements would vanish. The nucleus is a tiny, dense engine at the heart of every atom. What holds the nucleus together, despite the proton's fierce repulsion? The answer? The strong nuclear force, the most powerful force in nature. It acts only over tiny distances, locking protons and neutrons together with unbreakable strength. This force is the source of atomic energy, released in nuclear reactors and bombs, as described by Einstein's E-2. But the story goes deeper. Protons and neutrons themselves are made of quarks, bound by the strong force. Quarks come in types like up and down. Protons have 2 up and 1 down, neutrons 1 up and 2 down. The strong force binds quarks so tightly that they can never be isolated. Try to pull them apart, and you create new particles instead. It's like a cosmic elastic band. The further you pull, the stronger it gets. The force we see in the nucleus is just a residue of the even mightier force inside protons and neutrons. Quarks are forever confined, and this is the deepest level of matter we've explored. The strong force is the universe's ultimate glue. Another force works inside the nucleus, the weak nuclear force. Subtle and mysterious, it's essential for the universe as we know it. The weak force can change one type of particle into another, enabling radioactive decay and the creation of new elements. When a neutron decays, the weak force transforms a down quark into an up quark, turning the neutron into a proton and emitting an electron and antineutrino. Without the weak force, the universe would be almost entirely hydrogen. Its most spectacular role is in stars. The sun shines because the weak force allows hydrogen nuclei to fuse, starting the chain that powers stellar fusion. This process is slow. If the weak force were stronger, stars would burn out quickly, and life would never have evolved. The weak force sets the pace for stellar evolution, allowing stars to live for billions of years. It's the patient alchemist of the cosmos, forging elements and fueling the stars. The gentle sunlight that nurtures life is a direct result of this subtle force. The weak force is the quiet engine behind the universe's brilliance. The same fundamental forces inside atoms shape the universe on the grandest scales. The strong force binds nuclei, the weak force powers stars, and electromagnetism holds atoms and molecules together. Gravity, though negligible in atoms, becomes the master architect as we zoom out. Its reach is infinite, always attractive. Gather enough atoms, and gravity pulls them together to form stars, planets, and galaxies. The very small dictates the very large. The properties of atoms forged in stars determine the nature of planets and life. The light from stars is set by quantum leaps of electrons. Its journey across space is governed by electromagnetism. The life cycle of stars is written by the interplay of strong and weak forces. When we look at a galaxy, we see the collective effect of a trillion stars, each governed by the same forces as the atoms in our bodies. The universe is a unified whole. Laws that govern quarks also build galaxies. The journey into the atom is a journey into the cosmos itself. At the atomic scale, reality is ruled by quantum mechanics, a set of rules that defy our everyday logic. Here, particles like electrons don't have definite positions, they exist in clouds of probability, everywhere and nowhere until measured. This is superposition. A particle can be in many states at once, only choosing one when observed. The uncertainty principle means we can't know both a particle's position and momentum perfectly. This fuzziness is built into nature. Paradoxically, this uncertainty gives atoms their stability. Without it, matter as we know it couldn't exist. The Pauli exclusion principle prevents electrons from occupying the same state, creating the pressure that gives matter solidity. Quantum mechanics isn't just abstract theory, it's the foundation of chemistry and the reason materials have their properties. The strange, probabilistic world of the atom is what makes the universe rich and varied. The rules may be bizarre, but they are the source of all structure and stability. The quantum dance is the heartbeat of reality. Our journey into the atom reveals a universe as majestic as the night sky, built from emptiness, forces, and the strange rules of quantum mechanics. Everything we cherish, solidity, warmth, life, emerges from this hidden world. The quest to understand the small is inseparable from understanding the vast cosmos. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all forged in ancient stars. We are made of stardust, living collections of atoms on a cosmic journey. The universe's laws connect us to everything from quarks to galaxies. The wonder isn't just out there, it's within us. The journey of discovery never ends.